So we left off on Wednesday on Directories and Links chapter. Yesterday, Thursday, I basically didn't have any time to read or stream. It's a bit of a chaotic day for me. And today I have a birthday party that I'm going to, birthday dinner in the evening. So I don't have a lot of time, but I figured I'd hop on and hopefully I can get through directories and links and monitoring file events. This one actually seems interesting to me. This directory stuff I feel like won't be terribly interesting, but we'll see. All of it's stuff that I'm very familiar with already, but we'll see. Yeah, and that'll set me up for the weekend for starting on signals. Yeah. Alright, let's see how far I can get. I will need a break for lunch, and I will need a probably break for lunch at noon, and then I'll probably stop streaming at 4 today. Maybe a little earlier, maybe like 3:30. Just because I need to get up to Denver for dinner. So, all right, let's pick up where we left off here with readdir. The readdir function is a variation on readdir. So readdir, so it's a reentrant version. The key semantic difference between readdir and readdir is that the former is reentrant while the latter is not. This is because readdir returns the file entry via the caller allocated entry argument, while readdir returns information via pointer to a statically allocated structure. We discussed reentrancy in sections 21.1.2 and 31.1. We've already looked into reentrancy with respect to glibc, so I'm pretty good understanding of all that stuff. Given dir p, which is a directory stream previously opened via opendir, readdir r places information about the next directory entry into the direct structure referred to by entry. In addition, a pointer to the structure is placed in result. If the end of the directory stream is reached, then null is placed in result instead, and readdir r returns 0. On error, readdir r doesn't return -1, but instead returns a positive integer corresponding to one of the error no values. On Linux, the dname field of the direct structure is sized as an array of 256 bytes, which is long enough to hold the largest possible file name, although several other Unix implementations define the same size for dname. sus-v3 leaves this point unspecified, and some Unix implementations instead define the field as 1 byte array, leaving the calling program with the task of allocating a structure for the correct size. When doing this, we should size the dname field as 1 greater for the remaining null byte than the value of the const name max. Portable applications should thus allocate the direct structure as follows. So you declare a direct pointer called entry p, and then we declare size t length. Then we say, hey, the length is equal to offset of diremf with respect to dname. I don't know what offset of is. I've heard size of. Offset of. What is dname again? Let's do man offset of. Offset of a structure member. Oh, okay. So it's the dname field. Is the direct structure in the source in the text here? I don't see it. Oh yeah, it is. So direct, if we go back a couple pages here, it's just a inode t, so it's the inode number, and then a char array, char star, dname. So when we call offset of, we're saying, hey, give me the offset of that field. The macro offset of returns the offset of the field member from the start of the structure type. So in this case, it could be like 4 or whatever, depending on the size of the inode. So you say, hey, the length of the entire entry is going to be the length of that inode, basically. That's what you're saying when you say offset of, plus whatever the maximum name is for a directory entry, and plus 1 character for the null terminating byte. So then we malloc the length for the entry p and handle the case when malloc errors. Using the offset of macro defined in standard def, std_def, avoids any implementation specific dependencies on the number and size of fields in the direct structure preceding the dname field, which is always the last field in the structure. Okay, that's why they did that. The offset of macro takes 2 arguments, the structure type and the name of the field within the structure, and returns a value of type size t, that is the offset of the bytes of the field from the beginning of the structure. This macro is necessary because a compiler may insert padding bytes in a structure to satisfy alignment requirements for types such as int, with the result that a field's offset within a structure may be greater than the sum of the sizes of the fields that precede it. Oh, okay. That makes sense. So it isn't just the size of the inode field, or in whatever fields that might be in the struct that we're unaware of. It's also giving you the size of all the alignments, padding. File tree walking. NFTW. The NFTW function allows a program to recursively walk through an entire directory subtree performing operations, i.e. calling some programmer defined function for each file in the subtree. The NFTW function is an enhancement of the older FTW function, which performs a similar task. New applications should use the NFTW, new FTW, because it provides more functionality and predictable handling of symbolic links. SUSV3 permits FTW either to follow or not follow a symbolic link. SUSV3 specifies both NFTW and FTW, but the latter function is marked obsolete in SUSV4. The GNU C library also provides the BSD-derived FTS API, FTS open, FTS read, FTS children, FTS set, and FTS close. These functions perform a similar task to FTW and NFTW, but offer greater flexibility to an application walking the tree. However, this API is not standardized and is provided on few Unix implementations other than BSD descendants, so we omit discussion of it here. A lot of the APIs in like libc and even the kernels, syscall table, you can just see the history, like the legacy that has preceded like what is currently, the best practice or whatever, or recommended practice, and it's all for compatibility, which makes sense. Like, you don't want to break binaries and break source code. That's like a big no-no in the operating system world, but it just leaves like a lot of this cruft lying around. I mean, you don't have to use it, so it's not hurting anyone. People who use it for compatibility reasons get value out of it, so it's helping people, it's not hurting anyone, but it is kind of like ugly just having all this kind of like garbage laying around, these APIs that no one ever uses if they're greenfielding something. I can only imagine how bad the Windows libraries and syscall table are, given how much insanity and compatibility that they've gone through over the past many decades. I'm sure it's intense, because they're, from what I understand, I mean, I don't do Windows stuff, but they're hyper dogmatic about compatibility, which I guess Linux has been for at least the past 15 years, maybe longer. The FTW function, or at least on ABI compatibility. The nftw function walks through the directory tree specified by dir path and calls the programmer-defined function func once for each file in the directory tree. So you say, hey, here's a directory path, not a... So it's a function, it's not a syscall, but you give it a path instead of giving it a directory stream or a file descriptor for the directory, which is odd because most of the library functionality uses directory streams. But I guess this directory are not really reading itself, maybe. I don't know. Alright, so we give it directory path, and then we give it this function pointer that returns integer and takes in the path name to the either file or directory that's handling, and then it gives you back stat on that path. It gives you a type flag, which should be part of stat, I believe. So it's odd that they give it to you as a separate argument. And then struct FTW. So that's the FTW original function. I'm not sure what FTW stands for. Might be nice to know that as we're reading. So in libc, what does FTW mean? File tree walk. Oh, that's appropriate. So there's a file tree walk struct that you allocate and pass in a pointer to. And then in addition to their path and the function, there is a nopenfd. I'm not sure what that is, or nopenfd, and then some flags. Return 0, yep. Or the first error no value returned by a call to func. So any of these calls to the func can error out the entire walking process, short circuit it. Alright, by default, nftw performs an unsorted pre-ordered traversal of the tree, the given tree, pre-order, processing each directory before processing the files and subdirectories within that directory. But is it depth first search or is it breadth first search? We'll ask AI. In lib C is FTW or N breadth first or depth first traversal? You got this, ChatGPT. I believe in you. Depth first. Yeah, that's what I thought. It does depth first. So say you go into a directory. First the directory is handled. Then it goes into the entries of that directory. If any of those are directories and they're ordered at the top, then it'll hit that directory, and then the next directory. So go dep first, and just the ordering just happens to be whatever the kernel returns, I imagine, because it's unsorted pre-order traversal, which means that you don't traverse down and then handle things back up. You handle things as you're traversing down. While traversing the directory tree, NFTW opens. Let me close this out. NFTW opens at most one file descriptor for each level of the tree. The NOpenFD argument, so that's the number of open file descriptors, specifies the maximum number of file descriptors that NFTW may use. If the depth of the directory tree exceeds this maximum, NFTW does some bookkeeping and closes and reopens descriptors in order to avoid holding open more than n OpenFD descriptors simultaneously, and consequently runs more slowly. The need for this argument was greater under older Unix implementations, some of which had a limit of 20 open file descriptors per process. Modern Unix implementations allow a process to open a large number of file descriptors, and thus we can specify a generous number here, say 20 or more. Boop. The flags argument to NFTW, what is FTW again? Is file traversal walk. What was that again? Can't believe I forgot that already. File tree walk. File tree walk. The flags argument in NFTW is created by ORing 0 or more of the following constants, which modify the operation of the function. File tree walk change dir. Do a chdir into each directory before processing its contents. This is useful if func is designed to do some work in the directory in which the file specified by its path name argument resides. So it'll set its current working directory to the directory that it's in. Makes sense. FTW depth, do a post order traversal of the directory tree. This means that NFTW calls func on all the files and subdirectories within a directory before executing func on the directory itself. The name of this flag is somewhat misleading. NFTW always does depth first, rather than breadth first traversal of the directory tree. All that this flag does is convert the traversal from pre-order to post-order. FTW mount. Don't cross over into another file system. Thus, if one of the subdirectories of the tree is a mount point, it is not traversed. FTW fizz. By default, NFTW dereferences symbolic links. This flag tells it not to do so. Instead, a symbolic link is passed to func with a type flag value set to symbolic link, as described below. But why is it called fizz? Let's ask AI. Why is the why is FTW_PHYS called that? Physical, not logical. That's a stretch. All this stuff is not physical. We're not dealing with physics here. How would they use whatever? For each file, NFTW passes 4 arguments when calling func. The first of these arguments, path name, is the path name of the file. This path name may be absolute if dir path was specified as an absolute path name, or relative to the current working directory if the calling process at the time of the call to NTFW, if dir path was expressed as a relative path name. The second argument, statbuff, is appointed to the stat structure containing information about this file. The third argument, type flag, provides further information about the file and has one of the following symbolic values. This is a directory, this is a directory. So this type is not the same thing as a stat file type, the 4-bit file type. This is something totally different. It's the FTW file, the FTW type flag. So you got directory. This is a directory that can't be read. Post-order traversal of a directory, and the current item is a directory whose files and subdirectories have already been processed. Is a file of any type other than a directory or a symbolic link. Calling stat on this file failed, probably because of permission restrictions. The value in stat buff is undefined. That's fun. Just throw some undefined behavior in there, why don't you? SL, this is a symbolic link. This value is returned only if NFTW is called with the physical flag. SLN, this item is a dangling symbolic link. This value occurs only if physical was not specified in the flag argument. The fourth argument to func FTW buff is a pointer to a structure defined as below. So this is base and level, offset to base name, part of the path name, depth of the file within tree traversal. That could be useful if you're like, just as an example, doing like indentation printing. You could just look at the level and be like, okay, well, I'm 5 levels in, so I'll indent 5 levels, instead of keeping track of that on your own. The base field of this structure is the integer offset of the file name part, the component after the last slash of the path name argument of the func. The level field is the depth of this item relative to the start point of the traversal. Each time it is called, func must return an integer value, and this value is interpreted by NFTW. Returning 0 tells NFTW to continue the tree walk, and if all calls to func return 0, NFTW itself returns 0 to the caller. Returning a non-zero value tells NFTW to immediately stop the tree walk, in which case NFTW returns the same non-zero value as its return. Because NFTW uses dynamically allocated data structures, the only way that a program should ever prematurely terminate a directory tree walk is by returning non-zero value from the func. Using long jump to exit from func may lead to unpredictable results, at the very least memory leaks in a program. Yeah, no shit. So we got an example program here. Oops, sorry, I was reading the wrong page there. Let's take a look at it. So this is just doing some printfs for an error. This is a dir tree, returns an int. This might be the thing that the function that we might pass into our walk. So if we look at our walk down here, passing in dir tree, yep. This is the function that actually handles each one. We get all of our arguments as described before. We go into a switch based on the mode of the stat structure. Again, the stat structure could be undefined at this point, so you really do need to check the type here, I think it was. That encodes for FTWNS, because if your stat structure is not defined and you go start reading memory from there, you can get anything out of here. But yeah, we're saying, hey, if MT, what is that? Let's do man to stat. They don't have the constants here, no? They do have IFMT. I mean, obviously that's a common pattern, but I'd like to know what it actually means. Well, just do I do test.c, sorry. Main stat underscore ifmt. And we're gonna have to import the stat stuff. I think that's a stat constant, right? So if we go over here and just say man 2 stat, and I think this is what we want, systat. Oh. Go to definition. Okay, use bit to determine the file type. Let's ask ChatGPT on stat ifmt means what? inode file type mask. Inode file mask type. I mean, it's pretty obvious that's what it's doing in context here, but I just wanted to know like what this name meant. And they're saying inode file type mask, but it's ifmt, so it'd be inode file mask type. Strange. All right. So we switch on that, and then we just print out the type. So dash for regular file, D for directory, C for a, what is that? Character device, B for a block device, L for a symlink, P for a FIFO, and S for a socket. Probably Unix domain socket. The question mark if we don't know what type it is. And then we printf out a string. Based on the FTW flags. Just saying if it's directory, then we print out D. So we already know it's a directory from here. Type is equal to directory, then we do this, else we do this. Type is, oh, so this is like chaining them all together. I hate it when people do these things. These ternaries nested inside of ternaries. I mean, it's not hard to understand, but just like not easy to understand when you just look at it. But it does prevent, I guess, allocation, even on the stack, because you're calling printf and you're giving it like a pointer to a character buffer that's in like the data section. Which is like where all the constant string literals are stored, read-only data. So that's nice. Whereas if you had like a switch and assigned it to a variable, then at the very least you're like wasting some stack memory, like a size of a pointer. I think we're also probably doing some instructions that aren't necessary for doing loads and stores with that pointer. But I would imagine a smart compiler would be able to figure that out with optimizations and just optimize that away. doesn't seem like a hard optimization. So when you like write code like this, just kind of wonder like why. But his book is very much like compatibility with a bunch of legacy and portability and stuff. So maybe, I don't know. I just don't like these nested ternaries. But anyways, you just say, hey, if it's a directory, then we do that. If it's a directory that we couldn't read, then we do that. If it's a, what is this DP? I forget what DP is. Oh, if we're, that's the that first. Type is equal to F, which is a file probably, right? Yeah. Symbolic link dangling, and NS, which is stat failed. So in this situation, wouldn't you want to like not do the read here? Then here he says if the type is not equal to that, then we read the. Wait a minute, I thought the NS was a stat failed. Yeah, so that's this stat button. So he does a check here, but he doesn't do a check here. I don't like that. Then again, using the level for indentation, which I mentioned earlier. I didn't know that you could do this. That's pretty cool. So you say percent star S, and then you give it the level and a string. This is weird though, because that's an empty string. I've never seen that format specifier before. Maybe if we pull up a man page for printf, and then we search for percent star s, which of course has some like special meaning. So maybe we just search for percent s. It's not even there. Format. Oh, we're doing printf from the command line. So you want 3 printf. Percent %s. Star s. Oops, sorry. Star. Go to the top. Search for percent star. What is this thing doing? Search for here we go. Arguments must correspond properly after type promotion with the conversion specifier. By default, the arguments are used in the order given, where each star field within the see field width and precision below, and each conversion specifier asks for the next argument. And is there with the decimal integer m denotes the position of the argument list. I've never encountered this syntax before. dynamic field width feature together with a string format. Print a string S with a field provided at runtime. Field width provided at runtime. Dynamic width. Take the next argument, int. Use that as a field width. Okay. If the string is shorter than the width, it's padded with spaces. That's a behavior that I was missing. Okay, that makes sense. Print the base name. Okay. So in here we get opt. Cool. Pretty straightforward there. The programming listing 18.3 displays an indented hierarchy of the file names in the directory tree. One file per line, as well as the file type and inode number. Command line options can be used to specify settings for the flags argument used to call an FTW. The following shell session shows examples of what we see when we run this program. We first create a new empty subdirectory, which we populate with various types of files. So we create our directory, then we touch dir A1, or sorry, dir A and dir B, and then we link in A to dir S1. Wait a minute, there's no A. How does ln-sa how does that work? I don't think that's right. Let's do a test though. So I'm just jump to just gonna quit this out. I don't think I need that anymore. And then mkdir test. So mkdir dir touch dir A and dir B ln-sa dir S1. Okay, it says, hey, go to dir S1 and use this as a source. Okay, that makes sense. ln-sx dir DSL. That's a dangling. Okay. Okay, dir sub. Okay, touch dir sub x. mkdir dir sub 2. chmod 0 dir sub 2. Oops. Okay. And I'm going to go over here. I'm going to say mkdir chapter 18. And LA chapter 15. 14 maybe? Oh, 13. Rsync avzci chapter 13 slash to chapter 18 slash mv test into chapter 18 if I can. Move into there. In here, rm concurrent plot star test copy, and then rmrf build. Come on. Let's go ahead and open up ClangD, make this 18. Oops, not that it matters really. But, and then cd and ref. We got libs on nkdir. I'm going to grab this file here. 18. What was the name of it? It was nftw directory.c under dir's links. This one here. So I'm going to copy that link, make dir's links, and wget. And then we can cd back over to here, vim makefile, make sure that's correct. Looks great to me. This thing's still doing zig, which I suppose is fine. So let's make build. Wait a minute. There it is. Okay. And I wanted to pass that test. Bam. So we got test. Sub2, this is the could not read because of the permissions. This is the, wait a minute, that's a, oh no, this one here. That's a symbolic link that we couldn't read. I thought this was also a symbolic link. Why does it show up as a file? Test. Dir. Yeah, S1 is a symbolic link to A. Why does it say file? Shouldn't F be... Oh, because I didn't pass in the right flags, I guess. Okay, so you run that. If the above output, in the above output, we can see, oops, sorry, let's go back here. In the above output, we can see that the symbolic link S1 was resolved. We then use our program to invoke nftw with a flags argument containing physical and depth. So depth, we're going to see the tree inverted, right? Yeah. So if I do this, but with -p and -d, and S1 is now a symlink. And we didn't follow it to find if it was dangling or not. From the above output, we could see that the symbolic link S1 was not resolved. Drink some of my protein shake here. That thing is nasty. All right. Let's see, I'm down here. The NFTW action return value flag, starting with version 233 glibc, permits an additional non-standard flag to be specified in flags. This flag, FTW action return value, changes the way that NFTW interprets the return value from calls to func. When this flag is specified, func should return one of the following values. FTW continue processing entries in the directory tree. As with a traditional 0, return from func. So that's like the default. Skip siblings. Boop. Don't process any further entries in the current directory. Resume processing in the parent directory. Okay, that's useful. Skip subtree. If path name is a directory, then don't call func for entries under that directory. Processing resumes with the next sibling of this directory. So you probably want to have the, what do they call it? you'd probably want to have pre-order traversal so you can hit the directory first before its children, and then you can make a decision. Skipping subtrees when you're coming back up, it's like, well, I already processed a subtree. I can't skip it at this point. I mean, I could, but it won't do anything. All right, so F2W stop. Don't process any further entries in the directory tree. As with a traditional non-zero, return from func. The value F2W stop is returned to the caller of NTFW. The GNU source feature test macro must be defined in order to obtain the definition of FTW action return value from FTW.h. The current working directory of a process. A process' current working directory defines the starting point for the resolution of relative path names referred to by the process. A new process inherits its current working directory from its parent. Retrieving the current working directory. A process can retrieve its current working directory using get current working directory. The get current working directory function placed a null terminated string containing the absolute path name of the current working directory into the allocated buffer pointed to by CWD buff. The caller must allocate the CWD buffer to be at least size bytes in length. Normally we would size CWD buffer using the path max constant. On success, get current working directory returns a pointer to current working directory buff as its function result. If the path name for the current working directory exceeds size bytes, then get current working directory returns null with error node set to E range. On Linux x86 get current working directory returns a maximum of 4096 bytes. If the current working directory and current working directory in size exceeds this limit, then the path name is slightly truncated, removing complete directory prefix from the beginning of the string, which is still null terminated. In other words, we can't use get current working directory reliably when the length of the absolute path name for the current working directory exceeds this limit. In fact, the Linux get current working directory system call internally allocates a virtual memory page for the return path name. On the x86 architecture, the page size is 4096 bytes, but on architectures with larger page sizes, e.g. alpha with a page size of 8192 bytes, get current working directory can return larger path names. So yeah, I've noticed this morning my reading is a lot slower. I guess I'm kind of tired. It is nice to kind of just read slowly though. But yeah, I do feel kind of tired. When I read fast, I do miss things. Whereas like this morning, reading slowly, I'm not really missing anything. Not that this stuff is super duper interesting. But all right, let's continue. If the current working directory buffer argument is null and size is 0, then the glib wrapper function for the get current working directory allocates a buffer as large as required. It returns a pointer to that buffer as a function result. To avoid memory leaks, the caller must later deallocate this buffer with free. So why wouldn't you use that and just say, hey, glibc, I don't want to pre-allocate the buffer. You just allocate it for me and I'll free it. And I don't have to worry about like how big it is. You're going to take care of that. I don't know, I'd prefer something like that. Reliance on this feature should be avoided in portable applications. Most other implementations provide a similar extension of the Costudying specification if current working directory buff is null, And get current working directory allocates size bytes and uses uses this buffer to return the result of the caller. The glibc get current working directory implementation also provides this feature. The GNU C library also provides two other functions for attaining the current working directory. The BSD derived get current working directory path function is vulnerable to buffer overruns since it provides no method of specifying an upper limit for the size of the returned path name. The get current dir name function returns a string containing the current working directory name as its function result. This function is easy to use, but is not portable. For security and portability, get CWD is preferred over these two functions. Oh, it's get WD, okay. As long as we avoid using the GNU extensions. Okay. With suitable permissions, roughly, we own the process or have the cap sys ptrace capability. Wait a minute, hold on. So I guess what they're saying there, if I understood this correctly, is that if it's allocating the buffer for you, that there could be this buffer overrun vulnerability. I think that's what it's saying. The GNU C library also provides two other functions for attaining current working directory. BC get working directory path is vulnerable. No, it's just saying that it's vulnerable. And to use get current working directory. Okay. With suitable permissions, roughly, we own the process or have the cap sys ptrace capability. We can determine the current working directory of any process by reading the contents of the Linux specific procpid current working directory symbolic link. I think there's like a read link. And we do proc self current working directory. Yeah. But if we do like 1, it's like, no, no, no. You're not allowed to do that. No, no, no. You get the idea. But if we sudo read link, it's at root. It is interesting that current working directory is global state. It's probably stored on the task structure in the kernel, if I could venture a guess. But it is global state. So if you have like multiple threads, do they get their own current working directory? We could test that. But just a vim, we'll say multi-thread or multi-threaded get. Oops, go away, please. So annoying. Please go away. Can you go away? There you go. Threaded get current working directory .c. Here I'm just going to do main. Pull this thing up. I think I need include standard lib.h to get the exit constants. And then of course the formatter messes everything up. And then I go in here and I say, hey, just going to ask AI to do this. Write me a simple function that spawns 2 threads and waits on them in C. Okay, so we have to, I do want to get some miles writing code like this, so I'm just going to write it out myself. Include pthread. I think that stands for POSIX thread, pthread.h. Yeah, we'll take the we won't take the standard IO just yet. I guess, yeah, let's go and take it. Why here, actually up here, we need to declare our void star thread func thread void star arg. I don't really want that, so I'll just do that. Here we'll just printf. We'll do a char star here. Char star num thread ID. Here we'll just printf, and we'll pass in the thread ID. Okay, and then return null. And then here, oh, can I not pass it? Okay, we'll do it as a void star then, and we'll do d here. Long ID is equal to a long of arg thread ID. And then in here, we got our two p threads, T1 and T2. Sorry, p thread T. If pthread create is not equal to 0, pass it a reference to T1, a null, I don't know what that is, the thread func, and void star of 1L. There we go. This is adders. P error T1 failed to create. Exit, or we say just return exit failure. And I'll do it again for T2. And then over here, I'll just pass in this argument as 2. Why not? I'll say T2. So we got two concurrent threads now. And then we need to join them. So you say pthread join T1 null T2 null. So we're joined up. Okay, looks good to me. So these things, I want to do a write to current working directory. So we'll say, hey, I want to set my current working directory. So if I open up a new terminal and say man to set current working directory, is that a, so we do have get, but that's standard library, it's not 2, it's 3. Even though I said 2 here, it's like, nah, I know what you want. Set. Is there a set current working directory? It's chdir, that's what it is. Man to chdir. That is a system call. So I'm gonna change dir if it's not equal to 0. I like doing less than 0. Just say, hey, temp. If ID, or we'll switch on ID. And if we have case of 1, case, we'll have a default. Of course, you need a break in here. And then in here we say, we do our set to temp. This will require an exit of status failure, or exit failure. It's not set, it's chitter. And then I'll need to include the Unix standard.h. Chitter changes the current working directory of a calling process to the directory specified in path. Same thing, but with a file descriptor. 0 is returned, on error -1. Okay, so we can say it's not equal to -1. Sorry, not equal to 0. What am I doing here? Alright. So 1 is going to change it to temp. And then default is going to change it to root. If either of them are unable to do that, then thread ID, let me just do root here. %s, boom, do it again up here, temp, cool. So after it's chitter and after we join, then we'll do a root get is there a syscall for get current working directory? Then why does it not show up? Man to get current working directory. Why is there no man to page for get current working directory? What if I want to author a program with no libc dependency? How how would I read the current working directory? Okay, let's do the frickin' sys. I mean, I just wish there was a documentation for it. Like, how do you know how to call a syscall? Where would I find docs for syscall? Okay, whatever. Undocumented syscall. Great. So, what are we doing here? This guy? Yeah. Oh, but this uses the libs. Okay. Well, I'm going to use it anyways. And then I got to import syscall here. Oops. Okay, so we can say we need buffer, a char star buffer, which will say buff is a char array of path max +1, and then size. What is size? It's this thing, like it's undocumented. Who knows? Well, maybe there's documentation next to the symbol here. No, nothing there. Can't go to definition there. Okay, well, well, we look at the assembly, so what are the I guess I could just do path max +1 here. And that's going to give me back the character buffer, and I can say, hey, if that is not equal to 0, or is less than 0, I should say. So I think it might return the number of bytes written, who knows. Then we'll do our p error. We'll say, hey, your get current working directory syscall failed. Return exit failure. Okay. And then I'm going to do the same thing up here. I'm going to do on these threads. In thread. This will not be a return. This will be an exit failure. Okay. And I'll do a printf. And then we're just going to say right here. We're going to say, hey, write that. We wrote that, and then we read this. Buff. Oh, hopefully that works. And here we'll just say final read is that. Great. Up here now it's complaining that Uh, okay. Sorry, this needs to be just ID here. ID there. And this needs to be a long. Okay, and then this guy needs to be ID and a long as well. Okay. Go ahead and make everything. Build. Threaded get current worker. So one did its write and then did a read and got the wrong result. So it's, yeah. It's racing. There we go. You got a different result there. So in this situation, thread 2 ran first. It did its write. And then in between its write and its read, thread 1 did its write to temp. And then thread 2 did its read and got temp out. And then thread 1, of course, read temp, and its final read was temp. So that shows how this is unsafe. Vim main, or what is this thing called? Threaded. Oops. We'll just say up here. Well, this program just demonstrates how current working directory state is global to the process, not thread local, and that access to it needs to be synchronized, otherwise you could get erase it. Otherwise these threads would race. Actually, what I'll say here, this program demonstrates how is global to the process, not thread local, when ran, depending on thread scheduling. The result might be slash or temp. Yeah, that sounds good. Yeah, look at that. That's beautiful. Okay, let's kill this guy. Okay. That was a fun little program. And kill this. Where did we leave off? I actually don't remember. How do I... Show mod icons. Yeah, that's what I want. So I can ban, timeout, warn. Wait, I'm gonna ban this person. Y'all are just spamming stuff. Bam. Alright. It would be nice in YouTube if I could just get a live pop out that works. Live chat pop up. Okay, where do we leave off? We read this. Let's continue from here. Changing the current working directory. The chdir system call changes the calling process's current working directory to the relative or absolute path name specified in path name, which is dereferenced if it is a symbolic link. The fchdir system call does the same thing as chdir, except that the directory is specified via file descriptor previously obtained by opening the directory with open. We can use fchdir to change the process's current working directory to another location, and then later return to the original location as follows. So we open up read-only the current working directory as dot. Then we chdir to some path, and then we fchdir back to the current working directory that we started with, and then we close the file descriptor. The equivalent using chdir is as follows. So in this situation, we allocate a buffer as path max, and then we get current working directory to save off that buffer, and then we call chdir on some path, and then at the end we chdir back to that buffer. Operating relative to a directory file descriptor. Starting with kernel 2616, Linux provides. I'm curious when I compile that. Yeah, it probably does have libc in it. Anyways, operating relative to a directory file descriptor. Starting with kernel 2616, Linux provides a range of new system calls that perform similar tasks to various traditional system calls, but provide additional functionality that is useful to some applications. These system calls are summarized in table 18.2. We describe these system calls in this chapter because they provide variations on the traditional semantics of the process's current working directory. System calls that use a directory file descriptor to interpret relative path names. So the traditional analog yeah, I've seen all these at things like open at, read link at. Those are more common. In order to describe these system calls, we'll use a specific example. Open at, yeah. I've seen open at in my us tracing. Okay. Open at takes the file descriptor and a path name, flags, so on and so forth. So I guess the path name is interpreted relative to the file descriptor. That would make sense. Oops. The open-at system call is similar to the traditional open system call, but adds an argument dirfd that is used as follows. If path name specifies a relative path name, then it's interpreted relative to the directory referred to by the open file descriptor dirfd, rather than the relative to the process current work directory. If path name specifies a relative path name, and dirfd contains a special value at current working directory, then path name is interpreted relative to the process current work directory. If path name specifies an absolute path name, then dirfd is ignored. The flags argument of open at serves the same purpose as for open. However, some of the system calls listed in table 18.2 support a flags argument that is not provided by the corresponding traditional system call. Let's see how much we got here. We are not making much progress. I'm just so tired right now. All right. Ugh. Let's see. And the purpose of this argument is to modify the semantics of the call. The most frequent provided flag is @symlink nofollow, which specifies that if path name is symbolic link, then the system call should operate on the link rather than the file in which it refers. The link at system call provides the @symlink follow flag, which performs the converse action, changing the default behavior of link at so that it dereferences old path if it is a symbolic link. For details of the other flags, refer to the corresponding manual pages. The system calls listed in table 18.2 are supported for two reasons. Again, we explain using the example of open@. Using open@ allows an application to avoid certain race conditions that can occur when open is used to open files in locations other than the current working directory. These races can occur because some component of the directory prefix of path name could be changed in parallel with the open call. By opening a file descriptor for a target directory and passing that descriptor to open@, such races can be avoided. In chapter 29, we'll see that the working directory is a process attribute that is shared by all threads. So that's what we demonstrated in our little program there. Of the process, for some applications, it is useful for different threads to have different virtual working directories. An application can emulate this functionality using open@ in conjunction with directory file descriptors maintained by the application. You can use thread local storage, or you can store stuff on the thread stack, or store things on the heap referenced to by the thread stack. These system calls are not standardized in SUSV3, but are included in SUSV4 in order to expose the declaration of each of these system calls. The X-open source feature test macro must be defined with a value greater than or equal to 700 before including the appropriate header file. Alternatively, the POSIX source macro can be defined with a value greater than or equal to 2008-09 before glibc. The @file source macro needed to be defined to expose the declarations of these syscalls. Solus 9 and later provide versions of some of the interfaces listed in table 18.2 with slightly different semantics. Boop. Changing the root directory of a process. Chroot. Every process has a root directory, which is a point for which absolute paths, i.e. those being with /, are interpreted. By default, this is a real root directory. By default, this is the real root directory on the file system. A new process inherits its parent root directory. On occasion, it is useful for a process to change its root directory. A privileged process can do this using the chroot system call. Chroot path name. The chroot system call changes the process root directory to a directory specified by path name, which is dereferenced if it is a symbolic link. Thereafter, all absolute path names are interpreted as starting from that location in the file system. This is sometimes referred to as setting up a chroot jail, since the program is then confined to a particular area of the file system. SUSV2 contained the specification for chroot, marked legacy, but this was removed in SUSV3. Nevertheless, chroot appears on most Unix implementations. The chroot system call is employed by the chroot command, which enables us to execute shell commands in a chroot jail. The root directory of any process can be found by reading readlink, the contents of the Linux-specific procpid root symbolic link. Okay. So I guess one thing that I've gotten from this chapter is that like CWD and root are very similar. I've always conceptually imagine them to be very different things, with CWD being this like place where you're just bouncing around in the file system, and chroot being like more of a isolation thing. But really, I mean, they're both global or process global state that's maintained by the kernel that changes the behavior of how path names are interpreted. In the case of CWD, it's how relative path names are interpreted. In the case of root, it's how absolute path names are interpreted. And I guess the other thing with chroot is that you need a permissioned process, or a process with the capsys chroot to change. So it is more difficult to change. You need the privilege or the capability to change it. Whereas CWD is like any process could change its own CWD. But they are very similar. More similar than I had previously imagined, or previously had in my mental model. All right, the classic example of the use of chroot is in the FTPD program, the FTP server daemon. As a security measure, when a user logs in anonymously to FTP, the FTPD program uses chroot to set the root directory of the new process to the directory specifically reserved for anonymous logins. After the chroot call, the user is limited to the file system subtree under their new root directory, so they can't roam around the entire file system. This relies on the fact that the root directory is its own parent. That is, /... is a link to /. So that changing directory to / and then attempting cd ... leaves the user in the same directory. On Unix, some Unix implementations, but not Linux, allow multiple hard links to a directory. So that it's possible to create a hard link within a subdirectory of its parent. Or a further removed ancestor. On implementations permitting this, the presence of a hard link that reaches outside the jail directory tree compromises the jail. Symbolic links to directories outside a jail don't pose a problem because they are interpreted within the framework of the process new root directory. They can't reach outside the chroot jail. So the hard link stuff. So you can't have multiple hard links to a directory. What is that? Is there a test? Yeah, MT or CD in the test. Oops. Okay. Can I do ln dir2? Hard link not allowed for directories. Huh. I didn't know that. In Linux, can you create a hard link to a directory? What about mounting over? That would allow an escape, I think. So the loops in the file system is an issue. Sudo. No. Not allowed. Oh. Oops. Please stop. Please stop. What did I click on? This is so frustrating. What did I do? There, I don't know how I got it. Got it stuck in some type of print screen mode. I don't even know how I did that. Anyways, okay, Command W on that. Okay, good. Normally, we can't execute arbitrary programs within a chroot jail. This is because most programs are dynamically linked against shared libraries. Therefore, we must either limit ourselves to executing statically linked programs or replicate a standard set of system directories containing shared libraries, including, for example, lib and userlib within the jail. In this regard, the bind mount feature described in section 14.9.4 can be useful. Alright, I got 1, 2, 3, 4. About 4 pages left, plus a page of exercises and some source code. Alright, we're almost done with this chapter. I actually do like the chroot stuff. It's kind of like reminiscent of containers. The chroot system call was conceived as a completely secure jail mechanism. Was not conceived. Okay, I was gonna say, yeah, it was not conceived. To begin with, there are various ways in which a privileged program can subsequently use a further chroot call to break out of the jail. For example, a privileged cap make node program can use make node to create a memory device file similar to dev mem, giving access to the contents of RAM, and then from that point anything is possible. In general, it is advisable not to include set user ID root programs within a chroot jail file system. Even with unprivileged programs, we must take care to prevent the following possible routes for breaking out of a chroot jail. Calling chroot doesn't change the process's current working directory. Thus, a call to chroot is typically preceded or followed by a call to change dir after the chroot call. If this is not done, then a process can use relative path names to access files and directories outside the jail. Some BSD derivatives prevent this possibility. The current working directory lies outside the new root directory tree. Then it is changed by the chroot call to be the same as the root directory. If a process holds open a file descriptor for a directory outside the jail, then the combination of fchangedir plus chroot can be used to break out of the jail, as shown in the following code example. So we have our file descriptor. We open root as read only. Then we chroot into home. And then we just change dir back to the original file descriptor and then chroot again. Okay. To prevent this possibility, we must close all open file descriptors referring to directories outside the jail. Some other Unix implementations provide the fchroot system call, which can be used to achieve a similar result to the above code snippet. Even preventing the preceding possibilities is insufficient to stop an arbitrary unprivileged program, one whose operation we don't have control over, from breaking out of the jail. The jail process can still use the Unix domain socket to receive a file descriptor from another process, referring to a directory outside of the jail. We briefly explained the concept of passing file descriptors between processes via a socket in section 61.13.3. By specifying this file descriptor in a call to fchangedir, the program can set its current working directory outside of the jail and then access arbitrary files and directories using relative path names. Some BSD derivatives provide a jail system call. Yeah, like Solaris, I believe. Or no, jailing is BSD. Solaris was zones. Jail system call, which addressed the points described above, as well as several others, to create a jail that is secure even for a privileged process. Resolving a path name. The real path library function dereferences all symbolic links in a path name to a null terminated string and resolves all references to /dot and /dot to produce a null terminated string containing the corresponding absolute path name. The result string is placed in the buffer pointed to by resolve path, which should be a character array of at least path max bytes. On success, real path also returns a pointer to this resolve string. The glibc implementation of real path allows the caller to specify resolve path as null. In this case, real path allocates a buffer of up to path max bytes for the resolve path name and returns a pointer to that buffer as the function result. The caller must deallocate this buffer using free. SUSV3 doesn't specify this extension, but it is specified in SUSV4. The program listing 18.4 uses readlink and real path to read the contents of a symbolic link and resolve the link to an absolute path name. Here is an example of the use of this program. So pwd, we're in our home directory. We touch X, we then link X to Y. We then view the symlink Y, where we do a read link on Y, which is to say X, and then we get the real path. Makes sense. I'm not even going to read the source code on that one. Parsing path name strings, dir name and base name. The dir name and base name functions break a path name string into directory and file name parts. These functions perform a similar task to the dir name and base name commands, which I've used many, many times. For example, given the path name so-and-so, dir name returns the directory, base name returns the base name, concatenating the string returned by dir name, a slash, and the string returned by base name yields a complete path name. Note the following points regarding the operation of dir name and base name. Trailing slash characters and path name are ignored. If path name doesn't contain a slash, then if path name doesn't contain a slash, then dir name returns the string dot. What is meant by that? If path name doesn't contain a slash, then dir name returns a string dot and base name. Okay, that makes sense. If path name contains just a slash, then both dir name and base name return the string slash dot. No, just slash. What? If path name contains just a slash, okay. Then dir name, okay. Applying the concatenation rule above creates a path name from these return strings, which yields the string slash slash slash. This is a valid path name because multiple consecutive slashes are equivalent to a single slash. The path name slash 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 is equivalent to the path name slash. If path name is a null pointer or an empty string, then both dir name and base name return the string dot. Concatenating these strings yields the path name dot slash dot, which is equivalent to dot, the current directory. Okay. Table 18.3 shows the strings returned by dir name and base name for various example path names. Cool. Using dir name and base name, I don't really need to read that. Both dir name and base name may modify the string provided to by path name. Therefore, if we use to preserve a path name string, we must pass copies of it to dir name and base name, as shown in listing 18.5. The program uses stir-dup, which calls malloc to make copies of the string to be passed to dir name and base name, and then uses free to deallocate the duplicated strings. Finally, note that both dir name and base name can return pointers to statically allocated strings that may be modified by future calls to the same functions. Summary. An inode doesn't contain a file's name. Instead, files are assigned names via entries in directories, which are table listings, file name, and inode number correspondences. These directory entries are called hard links. A file may have multiple links, all of which enjoy equal status. Links are created and removed using link and unlink. A file can be renamed using the rename system call. A symbolic or soft link is created using symlink. Symbolic links are similar to hard links in some respects, with the differences that symbolic links can cross file system boundaries and can refer to directories. A symbolic link is just a file containing the name of another file. This name may be retrieved using readlink. Symbolic link is not included in the target inode's link count, and it may be left dangling if the file name to which it refers is removed. Some system calls automatically dereference follow symbolic links, and others do not. In some cases, two versions of system call are provided, one that dereferences symbolic links and another that does not. Examples are stat and lstat. Directories are created with mkdir and removed using rmdir. To scan contents of a directory, use the opendir and readdir and related functions. The new file tree walker function allows a program to walk an entire directory tree, calling a programmer-defined function to operate on each file of the tree. The remove function can be used to remove a file, a link, or an empty link directory. You can also use unlink. Can't use it for empty directory though, just a file. Each process has a root directory, which determines the point from which absolute path names are interpreted, and a current working directory, which determines a point from which relative path names are interpreted. The chroot and chdir system calls are used to change these attributes. The get current working directory function returns the process current working directory. Linux provides a set of system calls, e.g. openat, that behave like their traditional counterparts, e.g. open, except that relative path names can be interpreted instead of using the process's current working directory. This is useful for avoiding certain types of race conditions and for implementing per-thread virtual working directories. The real path function resolves a path name dereferencing a symbolic link and resolving all references to dot and dot dot to corresponding directories to yield a corresponding absolute path name. The dir name and base name functions can be used to parse a path name into directory and file name components. Exercises. Let's see if any of these are things that I actually want to do. Let's see. In section 432, we noted that it is not possible to open a file for writing if it is currently being execed. Yeah, I remember that. Open returns -1 with error node set to eText busy. Nevertheless, it's possible to do the following from the shell. So we cco long runner C, we run the long runner, and then we make some changes to the source code, and then we compile it again. The last command overwrites the existing executable for the same name. How is this possible? So let's go ahead and do cd rmr test sudo, sorry. Blow that away. There we go. And then exercises.txt. And here we'll just do 18.1. The target binary file is unlinked, removed first, and then created with ocreat. The target binary file is unlinked. Remove first. Since the file data remains on disk, since it is still open. Once the process is done, once all the instances of the program are done running, it will be removed. In the meantime, the compiler is free to create a new binary with the same previous binary's name via something like create, and write whatever they want to that new file, since the inode number is, we'll say here, since the inode number is different, it has no effect on the old binary. There we go. And we'll just go, where are we at here? That's about 80 there. Bam. We'll just, oops. I think I want to space this in here like that. And then that'll put us at 84. So we'll do, oops. Target binary file is unlinked or removed first. The file data remains on disk since it is still open. Once all the instances of the program are done running, it will be removed. In the meantime, the compiler is free to create a new binary with the previous binary's name via something like create, and write whatever they want to that file. Since the inode number is different, it has no effect on the old binary. That's my story, and I'm sticking to it. Let's see what the answer is in the back here. I actually didn't read the whole question. Kind of jumped the gun on that one because it had a clue here. For a clue, use ls-li to look at the inode number of the executable file after each compilation. Yeah. Using ls-li shows that the executable file has different inode number after each compilation. What happens is that the compiler removes and unlinks the existing file with the same name as the target executable, and then creates a new file with the same name. It is permissible to unlink an executable file that is running. The name it removed is removed immediately, but the file itself remains in existence until the process executing is terminated. Exactly what I thought. 18-2, if that's a, yeah. Why does the call to chmod in the following code fail? So we make a directory test and we say, hey, we're going to give it the permission for user to read, write, and execute. And then we cd into the test. So now our current working directory is set to the test directory. Okay. And then we open a file descriptor, open the file my file, and we say, hey, I want you to have read write permissions on this file and create it if it doesn't exist. Sorry, I want you to read and write to this file and create it if it doesn't exist. And the user should have read and write permissions to it. Okay. And then we symlink my file to the parent directory in my link. That's safe. And then we chmod my link to allow the user to read, which removes write permission. So I would say you can't do that because you have, I mean, this is an educated guess, but since .mylink refers to my file and chmod follows the symlink, and my file is currently open with write permissions, the write permission bits cannot be removed. Not be removed. That's what I'm going to go with. Basically, like, you open it up with write permissions, and then you try to remove the write permissions on the same file effectively, because you're going through a symlink. And that's not allowed. Let's see. 18.2. The file my file is created and subject to test. The symlink call creates a relative link to the parent directory. Despite appearances, this is a dangling link. Oh. Oh, because my file, I got that one wrong. Okay. We'll say dot. Let's say my file is a or say my link is a dangling link, symlink, since its value is my file relative to the tester, not relative to the current working directory of the process at the time we created the. Well, actually, we didn't cd into it all. Let me say that. Okay, that makes sense. Despite appearance is dangling link, since it is interpreted relative to the location of the link file, and thus refers to a non-existent file in the parent directory. Consequently, chmod fails with the error no such file directory. A complete program containing the code of this exercise is available in the file so and so. Cool. All right. 8.3, implement real path. Don't care about doing that. 18.4, modify the program listing. 18.2, to use read. I don't care about doing that. Implement a function that performs the equivalent of get current working directory. A useful tip for solving this problem is that you can find the name of the current work directory by using opendir and readdir to walk through each of the entries of its parent directory. To find an entry, even reading this is annoying. Okay, implement a function that performs the equivalent of get current working directory. Well, I could just make a syscall. A useful tip for solving this problem is that you can find the name of the current working directory using opendir and readdir to walk through each of the entries in the parent directory to find an entry with the same inode and device number as the current working directory, i.e. respectively the STINO and STDEV fields in the stat structure returned by a stat and lstat. Thus, it is possible to construct a directory path by walking up the directory tree one step at a time, performing such scans The walk can't be finished when the parent directory is the same as the current directory. Recall that dot dot is the same thing as dot. Or slash dot dot is the same thing as slash. The caller should be left in the same directory in which it started, regardless of whether get current working directory function succeeds or fails. Open plus fchdir are handy for this purpose. Okay, I don't really care. Modify the program list in 18.3 to use the ftw depth flag. Note the differences in order in which I already. 18.6. It's just going to come out. The tree root is going to be at the bottom. AT7, write a program that uses an ftw to traverse a directory tree and finishes by printing out count and percentages of the various types, regular, directory, symbolic, and so on to the files in the tree. Implement an ftw. This will require the use of opendir, readdir, closedir, and stat system calls, among others. I'm not going to do that. In section 18.10, we show two different techniques using f, changedir, and changedir respectively to return to the previous current working directory after changing the current working directory to another location. Suppose we are performing such an operation repeatedly. Which method do you expect to be more efficient? Why? Write a program to confirm your answer. I'm not going to write the program, but I'll take a guess. It's 18.10. Let's go back here. It's page 363. Here. It's 18.10. So fchdir and chdir. So the fchdir one saves a file descriptor. So we have one system call here, two system calls, three system calls, four system calls. So there's four system calls here. So just on a system call number level, this has a level 4. Because we don't have to parse the path or anything, I think these system calls will be a little bit more effective. A little bit more fast to execute, because it's just like, okay, you give me the file descriptor, I can immediately get to the inode, versus having a path name. You have to like parse the string and convert it into a file descriptor or convert it to inode. It's slower to do that. So the equivalent is we allocate a buffer, which the compiler does that. We're not zeroing it out, so it doesn't matter. Then we get current work. So it's one syscall. This is three syscalls. So we say, hey, get the current working directory into this buff, change dir into some path, and then change dir back to the buff. So I'll venture a guess here. Let's see. This will be 18-9, and say that the chdir function take less time, might take less time considering there are only 3 syscalls. Oops. That it needs to make versus 4 with f chdir. However, f cheddar, the f cheddar version. Oops, we're at 40 there. Okay. F cheddar version only has to parse path names twice, and the cheddar version has to parse paths oh no, it's only twice on here as well. We'll say both versions only have to parse come on have to parse both versions only have to parse path names twice. So this one has to parse dot into whatever that means. Cheddar has to do the same thing for some path. This one has to parse some path and has to parse buff, but it also has to construct. However, we say cheddar. The cheddar version also has to construct a path and write it into the stack allocated memory. Given the costs of syscalls of the overhead of syscalls, I am going to lean on my intuition here and say, so that says 1, 2, 3, 4 versus 1, 2, 3. Cheddar is faster. Okay, 18.9. Using, yeah, I mean, my initial gut instinct was F cheddar would be more efficient. If we're performing the operation repeatedly within a loop, then with F cheddar we can perform one call to open before executing the loop. And with cheddar, we can place the. That's not what you said. Let's reread the question. In section 1810, we showed two different techniques to return previous working directory after changing current working directory to another. Suppose we're performing such operations repeatedly. That means the whole thing. That means open and close. Which method do you expect to be more efficient? Why? Write a program to confirm your answer. Then we were measuring the difference between the repeated calls to F cheddar and cheddar Calls to dir are more expensive for two reasons. Passing buff argument to the kernel requires a larger data transfer between user space and kernel space, and the path name and buff must be resolved to corresponding directory inode on each call. Kernel caching of directory entry information reduces the work required for the second point. Okay. Yeah, I'll just say here. If the FD is reused, then F shader version will be much faster. Doesn't have to resolve the path. I feel like his I feel like he didn't really like mention like, oh, you would be doing this in a loop where you reuse FD. Anyways, don't really care about that. Cool. Chapter 19. Boo boo boo. Okay, quit out of that. Let's go in and say vim readme. Oops, not the cd deck here. Vim readme. And we're going to create chapter 19. Oops. And this is going to be monitoring file events. Directories and links is now completed. Oops. Let's cd into chapter 18 and make clean. Everything else looks good here. ls-la ref. Does dirlinks cat ref dirlinks, does this thing pound include any of that stuff? Yeah, it does. Okay. Boom 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 boom. Okay. Oh, I need to fix that. Oh, come on. Okay, directories and links has now been completed. Chapter 18. Looks good. The make file never changes really at this point. It's generic enough. It's fine. That's my exercise answers. Ref, and then, oops. Go down here. This is the program that we wrote. This program just demonstrates how CWD state is global to the process, not thread local. When ran, depending on thread scheduling, the result might be /or/temp. Cool. Get CI, say finish chapter 18. Oops. Alrighty, and then 19. Let's just scan through this real quick. So 376. So close to getting to signals. So close. That's signals there. So 376 to 386. So just 10 pages. Tiny little exercise. It's actually, this stuff is way more interesting to me than the directory stuff. I guess because you spend so much time dealing with directories and files and stuff. It's like, okay, I've encountered this stuff a bajillion times. I'm not going to waste my time doing the exercises here. But with the iNotify stuff, it's really powerful, really interesting. All right, so if I go T here, T7 done, that puts us at 28% complete of the book. We're almost at 30%. All right, it is 11:51. I'm gonna go ahead and break here for about an hour to get some lunch in, and then I'll be back around 1 for a couple more hours to get through the file event stuff, and then we'll have all the file system stuff done. It's like we started like file IO buffering, but even up here there's like file IO stuff. Yeah, we had 2 chapters of file IO here, and then we had 1, 2, 3, 4, 5, 6 chapters of file IO stuff here. That's 8 chapters total out of the 19 chapters. So, sorry, I forgot to include this one here too. So that's 2 plus 1, 2, 3, 4, 5, 6, 7. So that's 9 out of 19, which I mean, about half. Half of the stuff we've been doing is like file system stuff. And this is the interesting stuff. So I'll be excited to get back on this at 1 after lunch, get through this really quick, and then I might break early to get ready for dinner, or I might get some work done on the beginning of the signal stuff. And I'm probably gonna be sick of signals by the end of this, but it's 1, 2, 3, yeah, three chapters on signals. Cool. All right, I'll be back in about an hour. All right.